So supposing you have a circle of inversion C. C is the circle of inversion. Okay. And let's say you have any geometric object, like you could have a point P. Then remember, under inversion P goes to P dash was our notation. Our new notation will be, it will be IC of P. Okay, IC of P means that under inversion with respect to C, P goes to P dash. Now we'll use both notations, P dash as well as IC of P. Sometimes it's easier to just call it dash when we label points, but sometimes we want to talk about what does inversion do to a line or a circle. So we already saw that if you have a line L passing through the center of inversion, passing through the center of inversion, okay, then IC of L is L. Okay, so now we want to sort of go further and see what happens to various other kind of geometric objects under circle of inversion. Okay, now before we do that, we want to actually discuss a quick prerequisite that's required to understand the next few parts. Okay, so the prerequisite is what's called the power of a point. Now inversion is an advanced topic, so you're supposed to know this power of a point, but let me quickly revise it for you. Okay, so power of the point is the following idea, that if you have a circle C, and if you draw two secants, okay, this is also called the intersecting secant theorem sometimes. If you draw two secants and let's say they intersect the circle at A and B and C and D, okay, and let's say these two secants intersect at P, then it turns out you can prove PA into PB is equal to PC into PD. Okay, I don't want to recall the proof, but the proof, if you want to know how it is done, it's just pretty simple. It simply happens because if you join AC and BD, then you can prove that triangle PAC is similar to triangle PDB, because when you have a cyclic quadrilateral, you have this angle equal to this angle, okay, and this angle is common, so therefore these triangle PAC and PDB are similar, and then use the ratio of similarity and you can get this. Okay, so anyway, so now the point is we have a very cool property now, right? Like you have basically, let's ignore the construction for now, it's not needed. So if you go back to this two secants, you notice that PA into PB is PC into PD. What this is proving is that if you draw any line passing through P, okay, EF, then again if you repeatedly apply, this will equal PE into PF, which means something really cool. Let L be any line that passes through P. Let L be any line that passes through P. That line can vary. When it cuts the circle at 2 points, the length P, let's say X and Y, then Px into Py is constant. You see, it's not changing at all. Alright. So the number that is not changing, that Px into Py, that number is called the power of the point P with respect to this circle. Okay. These quantities are called the power of the point P with respect to the circle C. Sorry, the circle notation is C. It's power of the point P with respect to the circle C. Now, by the way, this also works if the point P is inside the circle. Okay, so if you have a point P inside the circle, okay, and you draw any two chords, okay, and you have the same thing AB and you have CD, it turns out that PA into PB is equal to PC into PB. Okay, in this case also you call it the power of a point, whether it's inside or outside, this statement works. Now, if in the case when it is outside, this is a very important special case. Okay, and the special case is when you take this secant and keep moving it out until it simply becomes the tangent. As it becomes the tangent, you can sort of see that the points go and coincide. Okay, so it turns out that this is also equal to PT square. Okay, so the power of the point P with respect to the circle C is the length of the tangent square as well. Now, one of the key things here in this discussion is the converse. Okay, so one of the key things here is the converse. means the following. Supposing you have two lines, okay, and which intersect at a point P, and supposing there are 4 points, 2 points on one line, 2 points on the other, such that